I'm Prabhat. I'm a postdoc in the Center for Computational Sciences and Engineering. Today I'm going to talk about a new code, a GPU-accelerated 3D phase field simulation framework called FerroX for modeling and simulation of microelectronic devices which are made up of ferroelectric materials. We are developing this code within the Beyond Moore's Law microelectronics co-design program. This team has experts from material discovery and synthesis to device fabrication, all the way up to circuit and the system and architecture level design. Our group in particular within CCSE is responsible for modeling and simulation at device level. So we take material parameters and device parameters from our experimental colleagues, and we are responsible for predicting device level metrics, which will be used by circuit simulators and system and architecture designers. So this Beyond Moore's Law co-design program is designed to address the challenges of ever-growing power consumption in microelectronics. It has been predicted that by the end of this decade, microelectronics alone could get to up to 25% of the overall primary energy consumption. Especially with the growth of artificial intelligence and machine learning algorithms, the power consumption has just exploded exponentially. If we continue to use current CMOS technology, which take about 100 picojoules per operation, this is the trend, 25%. If we can reduce the power consumption per operation to attojoules per operation, then we can reduce this overall percentage from 25% to less than 10%. This conventional CMOS technology, which is the current state of the art, uses metal oxide semiconductor field effect transistors, or MOSFETs, as the fundamental building block. So these MOSFETs are characterized by this term called subthreshold swing, which can be defined as the amount of gate voltage required to cause one order of magnitude change in the drain current. And for transistor operations, we want the on to off current ratio to be pretty large. So it ends up requiring a large amount of gate voltage for operation. And if we look at the expression for subthreshold swing here, there is a fundamental lower limit of 60 millivolts per decade, because the term inside the parentheses is always going to be greater than 1, since this capacitance is naturally a positive number. So if you want to reduce the power consumption by this MOSFETs, we are looking for some ultra-low power MOSFETs, which can have subthreshold swing below 60 millivolts per decade. The 60 millivolt per decade lower limit is called the Boltzmann tyranny. So we are looking for something which can breach this Boltzmann tyranny. So in 2008, a new concept was proposed by one of our current collaborators, which could lead to sub 60 millivolt per decade subthreshold swing. So the idea here is to use a ferroelectric thin film in the gate stack of the MOSFET. And these ferroelectric materials are quite interesting quantum materials, and they have this famous double well energy landscape, the blue curve shown here. And if you look at the blue curve inside this rectangular region, the energy landscape has this inverted parabola profile. And in this region, it shows negative capacitance. But standalone negative capacitance is not stable. But if we connect a dielectric in series with the ferroelectric, then this inverted parabola can be flattened, and the effective negative capacitance of the ferroelectric can be stabilized. Now, if we aim to exploit that effective negative capacitance of the ferroelectric materials to reduce the subthreshold swing to below 60 millivolts per decade and to breach the Boltzmann tyranny. All right, so from modeling and simulation point of view, the first set of challenges comes from the overall nature of the problem. So if we look at this device, it is made up of different materials in different layers. For example, in the ferroelectric layer, we are interested in the evolution of the state variable called polarization. And throughout the device, we are interested in knowing the distribution of electric potential. And in semiconductor region, we are interested in knowing how the electrons and hole, the charge carriers, flow. And all this has to be done simultaneously and self-consistently. So it's a challenging multiphysics problem. The second set of challenges come from the computational efficiency side of things. So if we want to do a full 3D discretization of this ferroelectric field effect transistor, we would have, the problem will be computationally very expensive. especially if you want to resolve small-scale features. For example, some of these layers can be very, very small, so you want your resolution to be sufficient enough to resolve those features as well. And these ferroelectric materials have a lot of parameters. This device also has a lot of optimization parameters, like what should be the dimension of each material, and so on. So we are looking for optimal parameters for best device performance. So we want to be able to do a lot of simulations very, very quickly. We are also leveraging artificial intelligence and machine learning algorithms to do this optimization. And codes like ours are used to generate very large amount of training data, so you want your code to be very efficient and scalable. Before we started the development of this new code, we did quite an extensive review of what is currently out there. And the table here shows the current state of the art. The green circles show the available feature, and the red one show the missing feature. And I've listed 4 codes, 2 from academia and 2 from industry. The 2 codes from academia are from Penn State and Purdue, and the 2 industry codes are COMSOL and Centaurus. And as you can see, none of these codes have all the features that we want. The features that we are interested in is full 3D simulation of this multi-physics problem, extreme scalability, and on top of that, there's a problem of this open source. So none of these codes are open source, especially the codes from industry. You need to buy their license. If you want to be flexible in your modeling problems, you don't have that flexibility with codes from industry. So with all that in mind, we started the development of this code called FerroX, Ferroelectric Device Simulation at Extreme Scale, about a year and a half ago. So let's look at this code called FerroX. It's an open source, GPU accelerated 3D phase field modeling framework. It solves all the physical equations that I mentioned in the previous slide, in ferroelectric layer, in the overall device, and in the semiconductor region. It is a full 3D code. It is built using the exascale computing project library AMRX, which gives us exascale capabilities and performance portability. So you can run this code on your laptop all the way up to the largest supercomputers in the world. It is GPU capable, and we get about 15x speed up when we compare our CPU performance to GPU performance. And it is open source. You can check us out at the link shown here. All right, so let's look at the equations that we solved in FerroX in a little more detail. So in the ferroelectric layer, we solve for the polarization of the ferroelectrics by solving this time-dependent Ginzburg-Landau equation for ferroelectric polarization. And throughout the device, we solve the Poisson's equation to get the distribution of electric potential. And in the semiconductor region, we solve for the density of charge carriers by following this Fermi-Dirac distribution function approach. And all of this has to be done at every time step, self-consistently. We implemented second order accurate scheme in both space and time for solving these equations. And our accuracy, convergence and accuracy test shows that both polarization and electric potential indeed have second order accuracy in both space and time. To assess the performance of the code, we performed a weak scaling study. By that, I mean we progressively increased the size of the problem and correspondingly assigned more compute resources. And as you can see, the time taken per time step by the code stays the same. So we tested this on up to 128 nodes on Haswell CPU partition and on Perlmutter. And if you compare the time on the CPU and the GPU nodes, you can see that there's a 15x speed up on GPUs compared to CPU nodes. All right, let's get back to some physics now. So our goal is to simulate this entire ferroelectric field effect transistor. But the cool thing about this device is that we can simulate a portion of this device. That in itself is a device, and we can compare our results with experimental and other simulation codes. So we begin with a very simple problem. We simulate just the green layer in this device, the ferroelectric layer. So the device is essentially a ferroelectric capacitor. So we have a ferroelectric, on top we have a metal, and at the bottom again we have a metal which is grounded. And we set the potential at the top by applying the boundary condition to the Poisson solver. And we study the evolution of polarization against the applied electric field. And here I'm showing the plot of polarization versus electric field. And as you can see, the result, when we compare against experimental measurements, our results are in quite excellent agreement. All right, the second set of simulation that I'm going to show you is a little more complex. So we just add one more layer to the ferroelectric. We are now simulating both the ferroelectric and the dielectric layer. And in that case, as I mentioned briefly, this can result in a stable negative capacitance in the ferroelectrics, right? So when we look at the structure of polarization, it shows multi-domain. By that, I mean it shows periodic positive and negative values of polarization. And when we look at the potential distribution, we see that there is a maxima at the ferroelectric dielectric interface. And this maxima has value which is higher than even the applied voltage at the top metal. This is a signature of negative capacitance. So we indeed see a stable negative capacitance. And for this, we compared our results with published work. It is from 2020, and we have excellent agreement on that as well. All right, and finally, we did first full 3D simulation of the entire gate stack. So we have ferroelectric, dielectric, as well as the semiconductor layers. And for that, we see, first thing we see that the polarization is no longer just simple periodic structure, right? It has a complicated, more pattern which forms on the surface of the ferroelectric film, and it results in all kinds of things, which I won't be able to go into a lot of detail. But we see that on the surface of the semiconductor, there is a non-uniform distribution of potential, which will result in this different kinds of current voltage relationship when we do this simulation in full 3D. We also characterized, quantified the effect of doing this simulation in either 2D or full 3D, and we concluded that 2D simulations overestimate the effect of negative capacitance. For more details, I welcome you to read our paper, which we submitted a few months ago. All right, so our current effort is to model the entire device. One thing that is missing in our current simulation capabilities is to model the flow of current from source to drain. So for that, we are exploring multiple options, including Boltzmann transport model or non-equilibrium Green's function with quantum corrections. And we are also doing more simulations in collaboration with our experimental colleagues to help them design and fabricate these types of devices. All right, with that, I would like to thank you for your time. I would also like to thank my collaborators and all the developers and maintainers of AMRX and FerroX. Thank you.
Do we have any questions from the audience?
Great talk. I have a couple of questions. One is the last point about device optimization.
Mm-hmm.
So does FerroX already give you derivative information with respect to the device parameters?
So, I mean, we can implement if we don't have that feature yet. So that's the thing about developing our own code. But yes, right now the state variables, we just output the state variables. We output some derived quantity that we extract from the state variables. And the main quantities that we output right now are the polarization, the electric potential, charge at any point in the device. And soon we will be able to characterize the current versus voltage relationship across the transistor as well. And that is the quantity that that kind of is the main thing. It characterizes the transistor.
Okay. And then the second question, in terms of sources of variability or error, do you know from your experimentalist colleagues whether they can actually manufacture these things?
Yes. So some of these things have already been manufactured. Some of the things are being currently manufactured. And so, but the problem is when it comes to manufacturing these devices, every single time they manufacture these devices, the properties do not stay the same, right? So it's kind of hard to compare the variation of one parameter in simulations and variation of the corresponding parameter in experiments. But yes, they do have a large amount of data, and we are currently exploring some AI and machine learning techniques with our colleagues from Applied Maths department with our experimental colleagues to see if we can extract something from the patterns that they have measured. For polarization, for example, how the multi-domain patterns look in their images, we can extract something out of that using ML techniques. That would be great.
If you have more questions, please talk to Prabhat during the break. Let's thank our speaker once again.
Thank you.